Hello everyone and welcome back to the channel. In a distributed system where data is replicated across many nodes and updates can happen concurrently, how do you truly know the order of events? A simple timestamp isn't enough, especially when network delays or concurrent writes are involved. This is where vector clocks come in, a fascinating and a powerful mechanism for tracking causality in eventually consistent systems. In system design interviews, discussing vector clocks demonstrates a deep understanding of distributed data management. Today, we are diving into what they are, why they are crucial, and how they help solve consistency challenges. Okay, let's try to understand the problem. First, we have user 1, user 2, and we have node server 1, and let's say node A, node server A, and node server B. Okay? So in distributed systems, especially those that prioritize availability and scalability, like many NoSQL databases, updates can happen on a different nodes concurrently. Let's say that we have two replicas, node A and node B, holding users' profile. Okay? Let's assume that user 1 will update their email in node A to like new something at email.com or at gmail.com. And user 2 will concurrently update their phone on node B to like, let's say 5 something. Okay. Now, if node A sends its update to node B and node B sends its update to node A, how do they merge? This is easy. But what if user A and user B updates the same field and they update the same user? Say the status field, for example, to different values at roughly the same time. How do you resolve this conflict? And more importantly, how do you ensure that changes that casually happen before another changes are correctly respected, even if messages arrive out of order due to network delays? A simple timestamp won't tell you if two events happened concurrently or if one definitely happened after another. Okay, so this is where a vector clock comes into play. What is a vector clock? A vector clock is a data structure used in distributed system to determine the partial ordering of events and detect causal relationships between them. Unlike a single global clock or a simple timestamp, a vector clock is an array of map of process ID and counter. They just have process ID and counter pairs, and that's it. One for each process or node in the system design, or in the distributed design, not system design, sorry. Each entry in the vector clock, as you can see here, represents the logical time of the associated node from the perspective of the node holding the vector clock. Number 2, we have analogy. Instead of everyone having a single stopwatch, it's like every participant in a conversation has a list of stopwatches, one for themselves and one for every other person they have ever talked to, tracing how many times they have heard an update from each other. So as you can see, we have partition 0, 1, and 3. Okay, but I guess this looks this is not that easy, and I guess maybe my understanding of what is a vector clock, I guess, doesn't break the ice yet. So I guess we need to talk about how it works to fully understand it. So vector clocks involves based on 3 simple rules: initialization, local event, sending and receiving messages. Okay, what this means. First, we have the initialization. When a process or node, let's say P1, starts its vector clock is initialized with 0. okay, for all entries. Like it should be 0, 0, 0 for all entries. So for system with n nodes, P1 will start with 0 for all entries, okay? After that, we have local event, which is an internal activity. When node P1, for example, perform any local event, it increments its own entry in the vector clock. So it will be +1, as you can see here. You see this one? This signifies that node P1 has progressed. Okay? Number 3, sorry, which is the last one, which will be sending and receiving. As you can see, here it sends something, like this start with 0, and 2 here it represents for it. They have some internal process. They try to send and receive. So when they receive and updates from a specific P, like from a specific node, like P1, they will update their own clock. As you can see here, you can see this, comparing to this one, they update it. So you need to focus on this one because this is a trickier part. We have sending and receiving messages. When P1 sends a message to P2, it includes its current vector clock with the message. Okay? So again, B1 will send to B2 and it will have its vector clock with the message. In the receiving part, when node P2 receives a message from node P1 with its vector clock, node B2, this one, will perform to update to its own vector clock. First, it updates each entry in its vector clock to be the maximum of its current value and the value from the incoming messages. So it was 0, 1, 0, and we have 2. So we have updated, and there was another internal process, so 2, 2. Okay, again, it updates each entry in its vector clock to be the maximum of its current value and the value from the incoming message. Okay. Number 2, then it will increment its own entry. It was 0, 1, 0. It will get 2. And we add another one because it increments its own entry, representing its own progress after processing the message. Okay? So this is have like casualty check, like event. For example, we have event A will happen before event B if basically vector clock B1 and vector clock B2, or let's say that VA and VCA and VCB, if the VCA is less than VCB, meaning every entry in VCA is less than or equal the corresponding entry in VCB, and at least one entry is strictly less. Event A and event B are concurrent if their VCA less than VCB, nor VCB is less than VCA. If they equal each other, they have some sort of concurrent. Okay. Okay. So why vector clocks matter in this design? Vector clocks are incredibly important for designing robust distributed systems that rely on eventual consistency, especially in environments where concurrent updates are common. First, we have causality tracking. The primary use, they allow systems to correctly identify if one event happened before another, or if two events happen concurrently. This is crucial for avoiding invalid state transitions and presenting the logical order of operations across distributed systems. Number 2, conflict detection and resolution. If two writes to the same data item have vector clocks that are concurrent, like neither happened before or after, it means they are conflicting writes. System using vector clocks can then apply specific conflict resolution rules, like merge logic, like lost right wins, if deterministic or even pass conflicts to the application layer. For example, like Postgres, I guess popular NoSQL databases like Apache, Cassandra, and Riak use vector clocks for conflict detection, I guess. Number 3, we have eventual consistency guarantees. They help ensure that eventually consistent systems correctly converge to a single state by understanding the causal history of updates. Lastly, we have decentralization. They allow nodes to manage ordering decisions locally without relying on a single global centralized clock, which would be a bottleneck and a single point of failure. Okay, so let's talk about challenges and interview discussions. While vector clock is powerful, I would say it has its own trade-offs. First, the size. For very large clusters, vector clocks can become large in entries in increasing basically storage and message overhead. This is often mitigated by using techniques like version vectors or dotted version vectors, which only store entries for nodes that have actually performed an update. Number 2, complexity. Implementing and debugging systems that rely heavily on vector clocks is more complex than simple timestamps. Number 3, not a strong consistency guarantees. They ensure causality and help with conflict resolutions, but they do not provide strong immediate consistency like two-phase commit or consensus algorithms. They operate within an eventual consistent model. I would say in some interviews, bring up vector clocks when discussing eventual consistent distributed databases conflict resolutions, or how to track causality in decentralized system where concurrent writes are possible. It demonstrates a sophisticated understanding of distributed data management beyond just basic replication. So that's it for this video, and see you in the future.